All right, we finished up our reactions of alcohols. Now we're on to ethers. And here we have what happens when you treat an ether with excess HBr. So there's excess of this around. We'll even write that here, XS. So there's lots of that around. And what I really want you to focus on here is that we're not doing really anything new in this reaction. We are going through the exact same mechanistic pathway that we saw when we had HBr with alcohols. It just so happens that this time we have two R groups instead of a single R group. So I think it makes a lot of sense for you guys to try this mechanism on your own. You should be able to reason it out already without me even talking to you about it. So try that out, pause the video, then you're back. All right, you're back. Nice job. So first step with alcohols, whether you treat them with HX or sulfuric acid, the first step in any of those reactions is protonation of the oxygen. So essentially, we have an acid-base reaction as the first thing that occurs. So nothing's changed here. We have an oxygen. It still has lone pairs of electrons. It's basic. And we have an extremely strong acid, HBr. So the first thing that's going to happen is we're going to transfer one of those protons to that oxygen, which means we have essentially a good leaving group, right? What did we form with an alcohol? We formed OH2+. If you just kind of isolate one of the sides, and if this was an H, we have the same thing, right? But essentially the only difference here is that we have kind of two R groups, right? So we have two different types of places that the Br- could add to, right? If this was an alcohol, the Br- would add to one side and the leaving group would be kicked out. Now it can add to either side. If we're going to compare this to alcohols again, what kind of a leaving group do we have here? Yeah, it would be a primary leaving group on either side. This is a primary leaving group. This is a primary leaving group. So that bromide is going to, essentially both sides of that are going to react at the same rate because they're both the same type of leaving group. So the Br- would be attracted to either side because there's a partial positive on either of those sides. The negative flows to the positive. That adds there. And then the oxygen acts as a leaving group. So that would give us our alcohol. And then this that we saw right here form is one of our equivalents of that. So I'm just going to box that. So we've accounted for production of that alkyl bromide. What's going to happen next? Well, we have an alcohol and we have more HBr around. The same exact thing's going to happen. We're going to protonate that alcohol. We have now a good leaving group and Br-. This is primary, so we can't form that carbocation, so Br- is going to have to act as a nucleophile and do that SN2 type reaction in a single step. That generates the second equivalent of the alkyl bromide, and we have H2O that forms. Well, H2O isn't necessarily a product here because we also have more HBr around, right? We have excess HBr, and HBr is a stronger acid than hydronium ion, so this acid-base transfer would also occur, making the hydronium ion with the counter ion of Br-. So again, hopefully this all really made sense based on all those mechanisms that we've done so far. Hopefully you don't have to memorize, oh, when we take an ether and treat it with HBr, we cut here, put a bromine here, put a bromine here. You should be able to reason through that mechanism and figure out what the products are. So what about if it's not symmetrical like this? Doing that next. All right, so this is both a predict the product / draw that mechanism type of question. The mechanism is going to be a little bit trickier than the one above because we have two different things. So we have an order of cleavage question. So I think the best thing that you can do now is take a minute to pause the video and try to draw the mechanism, draw the products, and then come back when you are done. Okay, you did that. Great job. So with all these ether cleavage reactions with acid, really we're just adding halogens to the carbons that the oxygen was attached to. So we're going to have that alkyl bromide, and then H3O plus with Br minus as a counterion. But how does it happen? Because that's the more complex thing in this reaction. So again, same type of mechanistic logic here. We protonate that, and that gives us a good leaving group. So we have Br minus around, but the question that you guys should be thinking about now is this going to be the bond that cleaves first, or is this going to be the bond that cleaves first? And it should relate directly to what we learned with substitution reactions of alcohols. What substitution reaction happens fastest? A tertiary alcohol, a secondary alcohol, or a primary alcohol? Which one of those reacts fastest with HBr, HCl, HI? All right, hopefully you thought that through. We have a weak nucleophile / base, and they don't want to do bimolecular reactions. They're really weak. If they're forced to do bimolecular, they will, but it's going to go really slow. They want to have a really strong electrophile, something that's really reactive for them to add to. So if the oxygen were to take the electrons away from the CH3, it can't do that, right? Because this would be a primary carbocation all by itself, no stabilization. That's too high energy. It won't happen. But if we pulled electrons away from that torpedo group, that would form an extremely stable carbocation, the tertiary carbocation, which is one of the most stable types, right? So that's what's going to happen first. This bond cleavage happens before that bond cleavage, and that's really important that you understand that. So that would form OH with that CH3. I drew in the CH3 for the first time, but nothing really new there. And our carbocation, then that Br minus would add to that carbocation. That makes that guy there. We have more HBr around. That HBr reacts the same way that we saw in the last mechanism. We form our good leaving group. We don't have the ability to form that carbocation, so in this case, it has to react in that slow SN2 type mechanism. So Br is going to add there, going to make that plus H2O, which if we have H2O plus HBr, the equilibrium is way to that side. So that kind of walks through the rest of the mechanism. Same idea as last time, but we have to wrestle with the idea of what side reacts at the fastest rate. So that's reactions of ethers.